Okay, welcome to this talk. I'm Bo from Naka University, and my talk is about modeling fluid-solid mixture with smooth particle hydrodynamics, namely SPH. Yeah. Well, the real-world multiple fluid phenomena is very common, and we can observe whether it's interfacial flow or some miscible or dispersed fluid mixtures in our daily life. These are some pictures I just downloaded from the internet, and we can observe such as oil-water mixture on the bottom right, or cocktail wines on the bottom left. These phenomena are very common in our daily life, and simulating multiple fluid has a long history in computer graphics communities, and there is a decent variety of researches ever since I think ever since 2003. Actually, first of all, the very first papers are on interfacial flows, and later or recently since 2014, there are some miscible. Since 2010. There are some miscible flow works, and these works are concluded in a survey we previously wrote, and if anyone are interested, you can just refer to it. And today I will talk about using SPH, namely the particle-based method, to model the multiple fluids. Well, the fundamental equations to calculate the multiple fluids is they are just like this. The multi-fluid Navier-Stokes equations. Well, these are the phase-wise equations. The continuity equations on phase K, and the momentum equations on phase K as well. So comparing with the single fluid equations, we can find that there's a alpha K value term in this equation, which is the concentration, or more specifically, the volume fraction of this multiple fluids. Well, the volume fraction concept is very easy to understand, because our air, we are breathing the air, it contains about 21% of oxygen and about 79% of other gas. So this is the concept of volume fraction. And but well, if these phases can mix together, well, we will call them a miscible flow. If they cannot mix together, we will call them an interfacial flow. For example, the mixing of oil and water are interfacial, because you can find a lot of interfaces between these two phases when they move. And if you mix, for example, alcohol with the water, you will see no interfaces within it. Or if you look at a cup of cocktail wine, you will see you will see mostly no interfaces between the colors. So traditionally in computer graphics, the interfacial flows are dealt very easily with the single phase equations, because you can just treat each region that contains one phase to be guided with a set of single phase Navier-Stokes equations, and you just need to handle the boundaries or handle the interfaces. You can track the surfaces, or you can handle the boundary conditions to get a good simulation of these interfacial flows. But if they can mix together, the things become more complicated, and we will talk about the mainly talk about the miscible case, and mainly in Lagrangian methods, because well, in in CFD field, in CFD computational fluid dynamics, they have simulated the miscible phases in grid-based methods for decades. So I will talk about our graphics approaches in particle-based methods, which are friendly to parallelize and faster. Well, as we just have seen that on the base level, there is a set of full multi-phase model. You need to calculate the phase-wise equations of the Navier-Stokes equations, and this model is we can call it the full multi-phase model. Is very most fundamental, but it has the drawback to that it's hard to complete. You usually need many assumptions to complete these equations and get an implementable algorithm. Well, with some simplification, you can have the mixture model, the so-called mixture model, and this mixture model has the this mixture model has the feature that it can analytically compute the relative velocity between these phases, and the mixture change, the mixture values will be computed from this relative velocity directly, and have some miscible flow effect. And finally is the homogeneous model, and this model assumes that we have some all the phases are moving with the same velocities, and this model is the easiest to compute, but it also discards some important effect that multiple fluid phenomena has. So I will talk about them one by one in the next talk. So talking about the traditional or conventional ways to for multiple fluid simulation, we can think about the simple diffusion models, which means that we just calculate the diffusion equation between the phase form fractions, and these form fractions will change according to time, and the diffusion equation will give us some good result, but it will not be enough for complex phenomena. And as I have mentioned, the homogeneous model will replace this diffusion equation directly in the red dashed line, and the mixed model will replace the calculations in blue dashed lines, which the mixed model will solve the continuity equations directly. So this is the mixed model. On the equation below is the momentum equation, the phase-wise momentum equation we have just seen, and if we sum them by one fraction of k, we sum the k equations together, and we will get a mixture momentum equation, which we use the aggregate or average velocity, average density of the mixture to have this mixture equation. Well, these terms in phase-wise equations will sum up to be the corresponding terms in the mixed model equations. And a similar summation applies to the continuity equation, which we will say that well, this continuity equation is very similar to the single phase one, but there's an important difference that we cannot assume the mixed model in the mixed model that the divergence of any velocity is 0. We cannot assume that. The reason I will talk about the reason in later slides, but now currently let us move on. Well, this similar summation is not very usable. It's not very useful in actual implementation. In the actual implementation, we use this kind of phase-wise equation derived from this phase-wise continuity equation, and the difference is that we use the average velocities here instead of the phase-wise velocities. So it's just some math derivations, and combining this continuity equation and the momentum equations, we can have the equations for the mixed model, and among them, this drift velocity can be analytically solved by some, well, this may look quite complicated, but each of the terms in it can be calculated analytically, such as the phase case density, which we can assume is constant, and the phase case pressure, which can compute it from the particle pressures in the SPH, and these are the volume fractions and mass fractions. So this drift velocity can be calculated analytically. And if we have this drift velocity analytically calculated, we see that if we use some explicit solvers, such as the most conventional SPH do, we can solve this. We can solve these continuity equations, and we can solve these momentum equations. So there is an example here. Originally, there are well, I think there is about 8 phases in this example, 1 transparent and 7 colored phases. So, well, this is the mixed model, and let's first move on to the homogeneous model. And let's think about the simple diffusion model. Well, the conventional simple diffusion model. What's the advantage and the disadvantages of diffusions in our solver? Well, the pros are the diffusion is very fast. It is very stable, and we almost always know how diffusion will go, how diffusion directions will go, which means it's very predictable. But the downside will be that the diffusion is non-reversible and unstoppable. You will never stop a diffusion before all the colors are mixed together, and the result is very, which results in a foul color. And well, a better model uses energy-driven mass dissipation instead of this diffusion. Well, you can think of it as a better diffusion model, which uses the so-called Hilliard model. And the equations are like here. The first 2 equations are what we the single phase, almost the single phase Navier-Stokes equations we are very familiar with. And the third one is, well, it has the form very similar to the diffusion model, which where we can see that there is a difference here. We have a mu k, which is chemical potential. It relies on the mass fractions and so-called Helmholtz free energy. This one, this Helmholtz free energy is something related to the physical state of the fluid mixture, which can be user defined, but it says that each state, the state is defined by the different volume fractions of each phase, such as we can say one state maybe if a three-phase mixture exists, we can define one state to be 0.3, 0.3, 0.4, and another state will be 0.2, 0.5, 0.3, which are the volume fractions of these three phases. And each state has energy. Each state is related to an energy using this Helmholtz free energy. One example is shown here, which means from the state 1, from the mass fraction 1, mass fraction 2, mass fraction 3, we can compute energy at this state. The in physics, there's a law that is any physical system tends to move from high energy states to low energy state. So so if we define this Helmholtz free energy to this form, the fluid system will tend to move to a mass fraction state, which meets the minimum point of this FC. On the right, we can see that there are two local minimums, which are the red dots, and the global local minimum is on the 0.5, 0.5 state. So we can predict that the final state, will be this one. If we see this red, green, blue color, if we render this red, green, blue color, we will see that an initial fluid mixture will eventually goes to the final state, which is the red will stand. Let's see. I think. I think the second state is rendered red. Red will stand out, and blue and green will mixture half by half. So this is the effect of Helmholtz free energy, and this is another result of mixing mixing two fluids together, which one is the egg yellow and the other one is the water. Okay. There's a recent adoption of this theory, which appears in Dr. Chen's 2020 paper. Well, their paper is on reducing calculation errors using MLSRK interpolation of the for the SPH simulation, and they used the NSCH equations for multi-phase concentration evolutions, and below are their results. So let me compare this this so-called mixture model or Navier-Stokes Helios model. Well, the energy-based model, which I just shown, is much faster because you don't need to calculate the phase-wise continuity equations. You just need to solve a diffusion-like equation, and that is all. So it's a bit faster, and it is theoretically easier to satisfy incompressibility, because you will see that the momentum equation is very similar to the single phase one, and it says if you assume each phase are moving at a if you assume all the phases are moving at the same velocities, the divergence of the velocity fields becomes 0 again. So you can just use such as PBF or any other techniques to that applies to single phase simulation to enforce incompressibilities in such works. And currently, the third one is that it applies to extraction, but it has also some drawbacks, which is the advantage of the mixed model. If we face this unmixing back motion, you will see that well, these several phases are actually immiscible, but originally we manually set them to be mixed in a mixed state. The SCH calculation will first produce dispersing drops before unmixing them into later layers, but the mixed model will be more natural. The result of mixed model will be more natural and in the layering process. So there are some side steps for this for these multiple simulation methods. The first one is that we can exploit volume fraction to have some post-simulation process according to the existing simulations, and because for especially for bubbles, I mean, so bubbles have this this feature that when you look at the because it's gas liquid mixture, when you look at the mass fractions, you will see that the liquid fraction, the fraction of liquid is dominating. But when you look at the volume fractions, you will see that the gas fraction will be dominating. So we can calculate this difference between this mass fraction and volume fractions, and re-render the existing simulations to generate bubble effect. Or we can see that we can add bubbles to existing multiple fluid simulations. This is a result. The second one is that we can integrate the multiple fluid concept into other physical systems, such as the shallow water equations, and to generate some dissolving surface effects. These are the equations we used in a previous paper, and this is a result. We can see that the bottom color will be dissolved during this water flowing, and it will stick to the solid surface when the water flows over this region. So well, I just mentioned that the homogeneous model has some advantages to enforcing incompressibility. Well, it also means that the incompressibility is an issue to the mixed model, because the compressibility. Well, there is a hard question: is that what is the incompressibility we are talking about? Now, if we think it in more more carefully, we can see that the compressibility can be physical. Because if we have reactions, if we have phase transitions, water can turn into gas in some extreme cases, or not extreme. We observe it in our daily life, but in our simulation, it's kind of extreme. This is certainly not non-physical. So what is non-physical incompressibility? Well, I think they are due to the numerical calculation errors in our servers, whether it's the drawback of the model, or whether it's the drawback of our implementation. So such non-physical incompressibility is what we want to eliminate. But for multi-phase flows, the physical compressibility is common, and we want to model them, or we need to model them in our simulation. So we need to tell them apart ultimately. But however, there are several methods currently to handle the incompressibilities in multi-phase simulations in SPH. The first method is using the homogeneous model. We just have seen it. The second method is that we change the definition of the integration velocities from the original integration velocity is balanced by mass, and or we can see the mass-weighted integration velocity. The new definition of this will be volume-weighted, or so we can observe the difference is that whether we multiply this UK with rho, or we can see that one integration velocity is the speed of the mass center, and the other is the speed of volume center. So if we use the new definition, we can prove that the new under the new definitions, we can prove the integrated velocity divergence will again be 0. So that will be a very good news. It seems a very good news because we can use previous single phase methods again, such as ISPH or the FSPH or etc. Well, during the process, we need to follow some similar derivation steps used by the previous definition, and derive a new momentative equation and new continuity equation. But this step is not very hard. So this method is adopted by Dr. Jiang in 2020s, and this is the result. Well, this is their result is very good, and the method is very practical for graphics use. But there's a problem. The advantage is that it is easy and simple, and directly use single phase conventions of incompressibility handlement. But the drawback is that this assumption is not very physical when we use the constant mass SPH. So let me show. Let us consider this toy example. If we have two phases, a green phase and a red phase. Green phase has a smaller density, and the red phase has a bigger density. And all the fluid are still. They don't. All the particles do not move, and they only depart from each other due to gravity, and in a immiscible phase, which means you will in the end you will see green particles above the red particles. Suppose originally they are mixed with 50% to 50%. So it's I use yellow dots to represent the initial particles. And finally, you will see that the red dots will lie above the the green dots will lie above red dots, and inevitably the green dots, the green particles will be will occupy a larger volume than the red particles, because the particle mass are the same, and the green ones have a lower density value. So what happens? In the green region, the volume expands, right? In the red region, the volume shrinks. So from the initial state to the final state, inevitably you will see some divergence during this change. So the actual physics is not divergence free when we use the SPH simulations. So the method 3 is that we proposed a method using deformation gradient, which do not assume any, which do not meet any divergence-free conditions. So we just think that the deformation gradient can be used on fluid simulations, and the Jacobian of the deformation gradient can be calculated by the volume fraction change of the of one particle. Because if we think of inside one particle situation, if phase case volume fraction is smaller than the last time step, it is equivalent to this phase is expanding within this particle region, within the matter volume represented by this particle. So we can prove that the JK, the Jacobian of the deformation gradient, local deformation gradient, corresponds to the volume fraction change rate. So this is derived from the continuity equation. And if we look at the momentum equation, we can directly compute a deformation gradient from this the physical definition. So we can match these two. Changes. One due to the velocity field and one due to the concentration change together, and derive a set of linear equations and solve it. So finally, we can integrate our method into readily into the IISPH framework as well. The final equations are very similar to the original IISPH single phase version, and we just saw a similar AP equals to B linear equation for the corrective P values on the particles. So these are the results. We can the figure in the red lines are our results, and the other two figures are from previous compressible simulations. So we can observe that the compressibilities are reduced, and the particle layering, and I mean the particles are much more ordered during the simulation as well, using our approach. This incompressibility works also has side steps, which mainly the method 2 assumptions are used in recent works, also by Dr. Jiang in 2021. He goes back to the fundamental full models and with the assumptions of his method 2, and proposed a direct solver to give more to give more rigorous results of the fixed mixing effect. So, well, another issue of the mixed model, or another issue of the multi-phase flows is solids. We want to put solids into the simulation with fluids together. So if we think of handling solids, or I can say handle sand-like solids, it's quite straightforward to add these solids into the mixed model by just adding one term into the momentum equations. This one is from the solid theory, actually from the solid model. You know that in fluid you will calculate the viscosity or the Gaussian, or the divergence of the Gaussian stress tensor. And in solid theory, there's a similar term. So just combining them together will lead to a mixed model which can handle solids. And you can add a dissolving equation to determine when and how much a solid can turn into fluid phase. So if I show it with a chart, it's just like this. You combine the SPH multiple fluids method and with SPH solid theories, and you can obtain a theory which can handle both solid and fluid together. And this is a video. So after pouring the water into the tank, you can see the coffee and candy are dissolved into the water. So there's an issue here because this solid model still assumes that the liquid follows the same NS equations when it mixes with the solid. Well, this is not a very big problem if we are treating with sand-like materials, because well, they can be considered as fluid as well when we trigger them. But this is not always the case, especially in if we are dealing with porous sponges. Inside the porous sponge, the fluid follows Darcy's law. It's not quite the same with the Navier-Stokes equations, and how can we handle it? Let us consider what can a mixture be first. So, or I can say, let us consider how can we exploit the mixed model. Well, firstly, a mixture can be a mixture of phases. Secondly, well, these phases can obey a mixture of physical laws, which can be different from each other, very different from each other. But thirdly, these phases can go freely across a mixture of so-called law regions. In each region, we have a set of different laws, and the phases obey these different laws according to the regions. Well, the problem is when we are using SPH, when we are using particles, we have one particle that contains several phases. How do we change a multi-phase particle state? Its positions, its volume fractions or phases, its densities, etc. when it goes across region boundaries. Or in more details, a sponge will absorb. Let us consider a toy example. A sponge absorbs phase A more quickly than phase B. In addition, they have different permeability values inside the sponge. For example, phase A can move much faster than phase B. Where should an SPH particle go on the boundary? And how is the concentration changed? And how can these two match with each other? Please note that if you move a particle on the boundary to a new place, ideally, if the particle is half out, half in the boundary, it should have 50% A, 50% B, or something like that. If as the particle moves inside the solid, the phase B should decrease. The volume fraction of phase B should decrease within this particle, and finally it will contain only the phase A volume fraction. So how can we ensure the consistency between this momentum change and or position change and the continuity or volume fraction change? So recently we just used we just did some research on this, and I will talk it about from the next slide. And before it, let's consider some simple approaches. Conventionally, for single phase particles, we can absorb single phase particles to when the particle meets the solid surface, and generate a new particle or add the particle mass to the so-called solid particles concentration. We can delete this, and we can insert new particles to when the liquid is squeezed out from the solid. But in the multi-phase case, it is very exhausting. First of all, you will delete fraction by fraction the particles, and when you insert a new particle, you will result in many more small or big particles with different sizes. It is very exhausting to handle in implementation. And if you add some merging or splitting strategies, it will be more complicated and not very stable in multi-phase case. And still, we want some fully coupling between multiple phases regions and with the solids. So how do we do it? We just solve this problem using the mixture model and introduce a concept of virtual phase. We will treat the in our work, we treat the inside and outside parts of the same phase as two virtual phases. So one phase will correspond to one inner phase and one outer phase in our simulation. And the action of liquid moving in or out and phase mixing or mixing are uniformly considered as virtual phase changes calculated by the mixed model. So all the problems, all the issues we mentioned in the last two slides are automatically solved by this mixed model kind of simulation with virtual phases. The the particle behaviors on the boundary are shown as in this figure. When the particle comes near the solid surface, in this case, we said that the yellowish phase can be absorbed, but the greenish phase cannot be absorbed. And the particle moves towards as the particle moves towards the solid surface, the light yellow phase, which is the outer phase, can change into the inner phase, which is the deeper yellow phase, and due to the absorption flux effect. And each phase is subject to one set of physics equations. The outer phase is subject to outer physics, and the inner phase is subject to inner physics. And the particle will be influenced by all the acceleration effects experienced by the phases from different laws. So and the concentration change is calculated by the mixed model itself. So these are the equations. The first two are the continuity equations, very similar to the original mixed model, and the last term is the boundary absorption flux. The third equation is the momentum equation of the particle, and all the there are several acceleration terms in addition to the gravity term. The second one is the pressure. The second one is the pressure term in the outer region. The third one is the pore pressure term, which is corresponds to the pore pressure due to the Darcy's law in the inner region. The fourth term is capillary acceleration in the inner region, and the final term is all other external forces. So this the right hand of this momentum equation is just adding all the effects together to influence the particle's mass center motions. There is a slight modification to the original drift velocity, but the original drift velocity in the original drift velocity calculation, there is a pressure term here, or I can say there's a term corresponding to pressure gradient here. Well, the Darcy's law, the QK is just a pressure gradient in the Darcy's law. So, no. The QK is proportional to the pressure gradient in the Darcy's law. So we can just use this QK in the Darcy's law to replace the original pressure gradient to make the inner drift velocity calculation completed. So the drift velocity calculations in the outer space are the same with the original mixed model. So we have this set of new equations. We solve them, and we can automatically solve all these issues, where and when, how, and how much particles move in and out, and how does the concentration change. So till now, I just talk about the Darcy's law, but this approach can extend to other more complex theories, because if we want to, if we look at the momentum equations, if we look at the momentum equation, we can see that, well, actually any effect will influence the fluid particles as an acceleration effect. It will appear as a different acceleration term or more acceleration terms. You can just add them in this momentum equation. On the other hand, these modifications, I just mentioned that I used the Darcy's law, I used the Darcy's law's value, which is proportional to the pressure pressure gradient inside the solid region to modify this drift velocity inside the solid region. If you are facing with other physical laws in other physical regions, well, any set of physical equations involving fluid almost always contain a pressure gradient driven effect. So you can just substitute them into this place, and you'll get new drift velocity calculations for that effect. So these modifications to the original mixed model is quite extensible, and it has the possibility to apply to more complex theories. These are some results of our work. So in both cases, the solid only absorbs the red liquid and leaves the green liquid outside. Well, originally on the left, the red and liquid and the green phases are mixed together, and on the right they are separated. So we have open sourced this work. Well, you can find the open source code on our homepage, and well, there's a final video. I think this open source code is the first multiple fluid open source one on the internet till now. So if you are interested, welcome to have a try. Thank you, and that's all.
Okay, thank you, Professor Bourrienne, for the talk. Any questions? Let's have a look at other questions. So any questions from the audience? Okay, if there's no questions from the audience, so I have several questions. Okay, so in this talk, initially you mentioned about the Navier-Stokes Cahill equation. Right? So are you using this in some of your research you mentioned here? Did you use this kind of a model equation to solve the multiphase flow problem?
Yes, yes. So this, do you mean this? Yeah. Actually, we published one. I just saw it in the last talk. One photo in the last talk. Yeah.
Okay.
We published one in 2015 on the graph.
Oh, okay, I see.
Yeah,
I see. Yeah, my question is that regarding this, my question is that so according to my knowledge, okay, the Cahill equation has a high order, the fourth order derivative equations. So it is more likely to have a large dispersion error during the simulation, right? So in the literature, there are some other formulations. For example, the Allen-Kane equation that can be replaced for the Cahill equation. So have you considered that kind of equation in your later research?
Well, not yet. To be simple, not yet. We have not considered them. Well, I agree. It's quite an interesting topic.
Okay.
But
okay. Thank you.
The issue is that those equations can what different effects can those equations bring? You know, these CH equations are pretty fast currently, and well, pretty stable, I think. And I'm not sure how much benefit will other models bring.
Yeah. For example, if you consider some kind of a more turbulent flows, whether this kind of lower order model can benefit for higher stability and accuracy.
Yeah, that's
yeah,
really
maybe this is a case.
Topic. Yeah. But another issue is that if you're using SPH, the turbulence, and you know, single phase SPH turbulence is not very well resolved yet.
Yeah.
So for multiple phase, it's more complex. So I think it's very interesting, and it deserves future research. Yeah.
Okay. And my second question is that you also mentioned about enforcing incompressibility in IISPH, right?
Yeah.
So I want to know that what's a key idea of this kind of incompressibility enforcement in IISPH, because you didn't mention that, and also how the incompressibility can be satisfied at a solid boundary, because I also saw some kind of coupling examples.
Yeah. It's my fault. I just omitted all those parts because they can all be found in the IISPH paper. So the IISPH, is for single phase. It's just based on single the divergence-free assumptions and or constant densities assumptions of the single phase fluid simulation. And the two works I introduced in this talk are for multiple phases, and actually we extend the we extend the theory, or we extend the framework to multiple phase. Yeah. So I can see that the boundary handling is also very similar to the IISPH one in the same form, but well, the full mathematical derivations are very complex. So it's not very easy to talk about them in these slides. But the final forms are very similar to the IISPH work. You can find them also in our papers.
Okay. And my final question is that, so have you considered about involving a grid into the solution process? For example, if you solve the concentration equations using a grid while you use a SPH for the fluid equations, so that may be, I'm not sure whether it will be beneficial or just the same.
Actually, it is also very interesting. We have not tested the grid, but well, this is quite similar to current hybrid methods, right?
Yeah. It's kind of a hybrid method.
So I think it will be possible to use some current approaches. Actually, there are some multi-phase SPH. No. There are some multi-phase MPM works. However, these works has some drawbacks that MPM can these multi-phase MPM works are using simple diffusion equations for the phase concentration change for the phase mixing effect. There are 12 papers in this NPM, use NPM. Yeah, I didn't put them into this size, which they're mostly done by the Tsinghua University, and they use simple diffusions, and well, there are some difficulties, I think.
Okay.
But I think well, difficulty. There are difficulties, but they deserve more research in the future. There are challenges,
Okay.
but there are opportunities as well.
Okay, I see. Okay, then I have no more questions. So,
Okay,
so see whether there are some more questions from the audience. So if there's no more questions, and then the session of this talk is here. So we welcome the two professors to give the talk today. Thank you.
Thank you.